Hi, my name is Tommaso Gagliazzi and today I'll talk about VFTGen, a tool to perform experiments in virtual fat-tree topologies. This is a joint work with Mariano Scazzariello and Lorenzo Ariemma. Nowadays, main online services are hosted in data centers, so they became a critical part of the internet infrastructure. Data center networks are complex since they are built using high-density architecture and present a high level of redundancy. Today, the most widespread topology in hyperscale data centers is the FAT-tree. But what is a FAT-tree? A FAT-tree is a special type of closed network. A typical FAT-tree is composed of 3 or more levels of switches. A tree-level design is composed by an aggregation layer that links together different points of delivery in short pods of 2 levels of switches. A pod is a set of leaves that are directly connected to the server farm, plus a set of spines fully interconnected to the leaves. Each switch has 2 K-ports, with K-ports pointing north and the other K pointing south. We denote by K-leaf the number of leaves ports pointing north or south, and by K-top the number of spines ports pointing north or south. The aggregation layer is composed by top-of-fabric switches, in short TOF, that provide inter-pod communication. A TOF is connected to at least one spine per pod. The number of links between a TOF and the top spine of a pod is called redundancy factor, denoted with R. This parameter divides the FAT-tree into types, single plane and multiplane. In single plane, each TOF is connected to all the top spine of each pod, while in multiplane, TOFs are partitioned into several sets called planes, reducing their redundancy factor in order to increase the maximum number of supported pods. This leads to a trade-off between redundancy and the number of supported servers. The complexity of FAT-tree networks make tests and experiments of new technologies in physical setups unfeasible. This is due to the high cost of the required equipment and the great number of human resources involved in the process. These factors limit the automation and the reproducibility of experiments, leading to a more error-prone testing pipeline. We present VFTGen, a CLI Python tool used to automatically build and configure virtual FAT-tree topologies. Generated topologies are ready to be deployed in Katara, a container-based network emulation system that supports both Docker and Kubernetes as virtualization technologies. VFTGen exposes a set of parameters to configure the desired FAT-tree topology and the routing protocol in a very simple way. Supported protocols are BGP, the standard de facto for FAT-trees, OpenFabric, a fluid optimization of ISIS, and Rift, routing in FAT-trees, an hybrid link-state distance vector protocol specifically designed for these topologies. For BGP and OpenFabric, we use FR routing daemon implementation. For Rift, still under standardization at IETF, we use the only currently available open-source implementation called Rift Python. Now, let's see how VFTGen works. To show how it's easy to install and use, this is a fresh installation of Ubuntu 20. Our tool has only one requirement, Katara. I already installed Docker on the system. Let's install Katara and Xterm from apt. Now, let's clone the VFTGen repository and we are ready. Let's create this simple FAT-tree topology in few seconds. We'll configure the topology with each of 3 supported protocols, and after I'll illustrate the configuration details and show some experiments. This is a simple JSON configuration file that specifies the required topology parameters. You can additionally specify them from the CLI. Open a terminal and run vftgen.py. This reads the configuration parameters and generates a directory. This directory contains a JSON called topology.info with all computed topology parameters. A lab.json containing information of all devices, including the device interfaces IP addresses and subnets automatically assigned by the tool. Finally, a lab folder with all the configuration files needed for Katara. This is a Katara scenario. As you can see, there's one folder for each device containing real routing daemon configuration and one .startup file containing startup commands such as interface configurations. Now, I'll briefly illustrate the configuration for each protocol. Starting from BGP, here's an example of Leaf configuration. We use state-of-the-art configuration derived from the BGP in the data center RFC. This is an OpenFabric Leaf configuration. We use ISIS best practices for data centers since this protocol is a variation of it. Finally, here is a Rift Python configuration file. Rift configuration is minimal since it supports zero-touch provisioning mode, and each node will fully configure itself after being started. Now, let's deploy a topology with Katara. So, I enter the lab folder and write Katara lstart. On the first run, Katara will install some additional components and download the required images. As you can see, it is very fast, and in few seconds you have a virtual FAT3 up and running. Here we have a terminal for each device to interact with it. You can do every kind of operation that you normally do on a real device. So, for example, we can start inspecting the routing tables or the interface IP addresses, and also dig into the control plane. Now, I'll open a web page hosted on server 211 using links from server 111. First, I start TCP dump on Leaf 101 interface ATH2, which is the interface connected to the server 111. This command writes a pickup file in the shared folder that is shared with the host. So, from server 111, I open the web page using links. Now, I stop the dump and you can find the pickup file into the shared directory of the lab. If I open it with Wireshark, you can see the HTTP requests of the web page. Now, let's see how the protocol reacts to a node failure. What I'll do is a ping from server 111 to server 211. The ICMP traffic in the first pod will traverse Leaf 101 and one of the two spines. I start TCP dump on spine 111 and spine 112 on the interfaces towards Leaf 101. Now I perform a ping from server 111 to server 211. As you can see, the traffic is forwarded to spine 111. Now I shut down the interface of Leaf 101 facing spine 111. The routing protocol reacts to the failure and after a minimal time of convergence sends the traffic to the other spine. Let's recover the Leaf 101 interface. The traffic is again forwarded to spine 111. This is only one of the possible experiments that you can perform with VFTGen and Katara. So, play with it if you are interested. VFTGen is an open source project and the code is available on GitLab. Thank you for watching!